Chapter 19, Applications of Integration, page 1. So we're talking about the area under the curve, which is something we've already talked about a little bit, so I don't think you're going to be surprised if you see that the expression, an integral, which calculates the area right here between a and b on the x-axis, underneath the function f of x, is going to look like this. The integral, the definite integral, from a to b of the function f of x with respect to x. Number 1, find the area of each of the regions described below by using first a geometric argument and then integration. Because these two that they're giving you, they're simple shapes that we can calculate the area with, middle school math. Okay? So instead of having a curved function that looks like this, we're just going to have a function y equals 5. If you remember, y equals 5 is actually just a horizontal line at height 5. And then they said that the x limits are x equals -6 to x equals 0. So it's kind of a rectangle here. The rectangle is 6 wide and it's 5 tall. So the area here is equal to 5 times 6, which is 30, right? So the answer, according to the geometric argument, is 30. What about integration? If we take the integral, we're going to make an integral that kind of looks like that. The integral from -6 to 0, we always put the left argument first and the right argument afterwards if we want to get a positive area here. The function is actually 5. When you take the integral of 5, it will be 5x. And then the book writes it this way. Definite integral from -6 to 0. So first we're going to put in 0, 5 times 0. And then we subtract the value when we put in the second argument, -6. And that gives us 0 minus a minus 30. So it's going to be positive 30. And it gave us the same answer as the geometric argument, which is what we should get. Next one. Y equals -3x. So this is no longer a horizontal line. Now it's a diagonal line. Looks kind of like this. It crosses the origin, and then it's got a slope of -3, which is actually much steeper than what I just drew here. It's kind of like this. Okay, and then we are going to evaluate it from -3 to 0. Oh, so I actually drew it on the wrong side. -3 to 0. So we're evaluating from here to here, and it kind of looks like this. Okay. So, -3, 0. And what's the height here? Well, if we put -3 into the function, we get -3 times -3, so it's 9. Okay, so we have a triangle that is 9 tall and 3 wide. So to find the area of this triangle, it would be 1/2 times 9 times 3. So it would be 13.5. And what if we took the integral of this function? Then it would be the integral of -3x from the limits -3 to 0 with respect to x. Remember that the integral of x is x squared divided by 2. And we're going to evaluate this definite integral from -3 to 0. First we plug in 0 and we just get 0. Then we subtract this, substitute with -3, so it's going to be minus a -3, and -3 squared divided by 2. And so that's going to be a positive 27 divided by 2, which is a 13.5. Same thing, right? So we got 13.5 using geometric arguments and also using the integral. Number 2, find the exact value of the area of the region bounded by y equals x squared, the x-axis, and x equals 1. Now, if you remember, y equals x squared is a parabola that has the vertex at the origin. So the reason why they didn't give two x limits is because since it goes through the origin, They only need one x limit. Do you see how like one of the x limits is the origin itself? So we could take the integral from the origin to x equals 1 of x squared dx. And so the integral of x squared is x cubed divided by 3. And we're going to evaluate it from 0 to 1. So first we plug in 1 and we get 1/3. Then we plug in 0 and we get 0/3 is 0. And the answer is just 1/3. What about the next one? The next one we're going to find the area bordered by y equals x cubed, the x-axis, x equals 1 and x equals 4. This is a little easier. We don't even need to draw it. They give us all the details. Okay? So the integral of x cubed is x to the 4th divided by 4. We're going to evaluate this definite integral from 1 to 4. So first we plug in 4 and we get 4 times 4 times 4 times 4, which is a huge number. Luckily we divide out 1 4 that's in the denominator, so it's actually 3 4s times each other, so that would be 16 times 4 is just 64. So that would be, when we plug in 4, we get 64. What about when we plug in 1? We get 1/4. It's going to be minus 1/4. So it's going to be something like 63.75. Okay? Alright. Now we're going to find the area between the x-axis and this is a quadratic above the y-axis. So the part of this that is above the x-axis. So they didn't give us the a and b this time. So now we need to use our chapter 1 knowledge to try to figure out where the x-intercepts are for this. Remember, the x-intercepts are going to be the roots. So if we can find the roots of this, then we're okay. And if you remember, to find the roots, we could use the quadratic formula or factoring. So let's try to do factoring first. So we got this. I'm putting it in the order of x, the x squared term, the x term, and the constant term. So you see I put it in the opposite order. Now I'm going to factor it. I'm going to get a negative x on one and an x on the other, of course. Then the 6, I'm probably going to have a 3 and a 2, because do you see how the middle term is just a 1, so it's probably like a 3 minus 2 thing there. And so, or maybe not. Let's try it. Okay, so we're going to put negative for both, and let's see what we get. So we'll have negative 3x, positive 2x. So that gave us the wrong sign. What if we switched it? So instead of 3 and 2, we'll put 2 and 3. 2 and 3. Okay, now we get negative 2x times positive 3x, and then, yeah, that worked out. Okay, so this is our solution for the x-intercepts. The x-intercepts are going to be x minus 3 equals 0. So the solution, one of the solutions is x equals 3. The other solution is negative x minus 2 equals 0. So that would be x plus 2 equals 0. So x equals negative 2. So our two numbers are negative 2 and 3. So we're going to take the integral from negative 2 to 3. And the function is going to be 6 plus x minus x squared. And then the integral of that is going to be 6x plus x squared divided by 2 minus x cubed divided by 3. And we're going to evaluate it from negative 2 to 3. So if we put 3 in there, we're going to get 18 plus 9 halves minus 27 thirds, which is actually minus 9. Yeah. And then we're going to plug in 2. So it's 2 times 6, which is 12. 2 squared over 2, which is 2. And we have 2 cubed over 3, which is 8 divided by 3. It's minus 8 divided by 3. Wow, that's a mess, huh? Okay, and so let's simplify that. So we have 18 minus 9. That is going to give us 9. We have a 12 plus 2, which gives us 14. We have a 9 minus 14, which is going to give us a negative 5. We have a 9 halves, which is a 4.5 plus 4.5. And we have a negative 8 divided by thirds, which is a negative 2 2/3. Oh, but it's a positive 2 2/3 because there's a negative there too. Okay, so then we have negative 5 plus 4.5, so that would be negative 0.5. And we're going to add that to the, oh, what a mess. Okay, so let's, I'm going to convert this back to a mixed fraction. So we got 8/3, positive 8/3. And then here we're going to have 1/2, or negative 1/2 plus 8/3. We're going to make a common denominator, which is 6. So we're going to have negative 3/6 plus 16/6 is equal to 13/6. I think that's the answer. All right, last one. So we're going to make a area. We're going to find an area between a hyperbola, the x-axis, x equals 1 and x equals 4. This is pretty straightforward. Remember, hyperbola kind of looks like this. X equals 1 to 4 is like this area here. So all we need to do is take the integral from 1 through 4 of the function 1 over x. And then the integral of 1 over x is log, natural log of x. We're going to evaluate natural log of x from 1 through 4. So we have the natural log of 4 minus natural log of 1. Natural log of 1 is 0, of course. So basically we're left with natural log of 4. Okay, and that's it for page 1.